Good day and welcome to Big Bad Tech. I'm Instructor Jim Pytel, and today's topic of discussion is circuit protection devices. Our objective is to take an introductory look at basic circuit protection devices. We'll introduce fuses, circuit breakers, ground fault circuit interrupters, and overloads, and we'll discuss their intended purposes, means of operation, and differences between them. Additionally, we'll compare and contrast high and low side switching arrangements, and discuss how system and equipment grounding relates to circuit and operator protection. Circuit protection devices are components that safeguard people and property from electrical and fire hazards. You are a circuit protection device. The simple act of just not doing stupid things is the first and most important line of defense when it comes to circuit protection. It is my intention that you understand, appreciate, and respect electricity, not fear it. It is as dangerous as it is useful, and there are laws, natural and man-made, that govern its wise use. Follow the rules. Follow the code. The National Electrical Code is there to safeguard people and property from electrical and fire hazards. Pay attention and don't operate devices outside their intended range, nor excessively overload them for sustained periods of time. If this advice is to be boiled down into a single standing order, let it be this: watch the current. Given our understanding of the power equation, we realize that power dissipated by a device is proportional to the square of the current through it. It is therefore understandable that it is of primary importance to maintain current at or below a certain predetermined level, since any increase in current constitutes a geometric increase in power dissipation. This is where not only a conceptual understanding of electrical theory, but also the proper use of instrumentation and numerical literacy come into play. It is incumbent upon any individual using any expensive electrical apparatus they wish to keep in working order to continually monitor current. For reasons I'll explain in later lectures, an overloaded or stalled motor will draw excessive current. The excessive current will heat up the wires. The hot wires will melt the electrical insulation or ignite it. The exposed conductors will cause more problems and more fires in an ever-increasingly bad positive feedback loop. Even with no circuit protection devices, such a situation is totally avoidable if you install and use equipment as intended and know how to use instrumentation. Pay attention and be prepared to shut it down any moment you observe unusually high current for a sustained period of time, smell or see smoke, or worse yet, see flames shooting from the system you're working on. Know where the off button is and make sure you've got access to it. Industrial systems often have a strategically placed emergency stop button that allows an individual observing an unsafe action or a scenario to immediately disable the system. Familiarize yourself with the location of these switches and know their intended purpose. Modern systems, however, cannot rely upon near constant human intervention. It is for this reason automatic circuit protection devices are employed. Additionally, I don't mean to discount preparedness, but I do need to temper your expectations because things can and do go wrong to even well-prepared people. Understanding basic electrical theory does not grant you invincibility. No amount of conceptual preparation on your part can prevent a faulted component from igniting the moment the power is turned on, nor can it prevent you from receiving an electrical shock from an exposed wire. The job of circuit protection devices is to prevent such problems from becoming injuries or damaging equipment. Today we'll take a brief look at fuses, circuit breakers, ground fault circuit interrupters, and overloads, all different types of circuit protection devices that all basically do the same thing. They are series switches that open up and stop current flow to prevent damage. They use different means of detection and operation, but ultimately they perform the same function. They stop current flow. Circuit protection devices are placed in series with the electrical load they are intended to protect because elements in series with one another carry the same current. This is the most fundamental of series circuit properties, and protection devices make use of this fact to selectively enable or disable current flow. If a protection device is closed, it allows current flow to the load, whereas an open protection device does not. Let's first introduce the fuse. A fuse is a metal alloy element that is purposely designed to melt a specified rated current and open the circuit and halt current flow. Here's the schematic symbol for a fuse. It is a two-terminal device placed in series or in line with a load that it is intended to protect. When the fuse is intact, the path between its two terminals is a closed 0-ohm path and the circuit operates as intended. An ohmmeter demonstrates this fuse is intact. When current reaches or exceeds a certain predetermined value for a certain amount of time, the fuse melts and the path between its terminal opens and stops current flow by becoming an infinite resistance. An ohmmeter demonstrates that this fuse is blown. Fuses, like hand grenades and your virginity, are one-time use only. When a fuse blows, it is rendered permanently inoperable. Fuses come in two varieties, fast blow and slow blow, which are indicators of their reaction time. When subjected to current above the rated value, a fast blow fuse melts and opens rather quickly. whereas a slow-blow fuse would take an appreciable amount of time to melt and open. A slow-blow fuse would allow a temporary surge of current, however would open if current remained in this elevated state for any length of time. The advantage of fuses is their incredibly simple operation principle. As long as the rated voltage and breaking capacity of the fuse is appropriate for the application, they are an inexpensive and reliable means of defense. This being said, a blown fuse is a non-reusable component. Because of this disadvantage, fuses often form the final but most reliable line of defense for circuit protection. If there is a line that absolutely must not be crossed, a fuse is there to figuratively burn down the bridge prior to letting the whole castle fall. Importantly, a blown fuse is not a sign that the fuse is at fault. A blown fuse means the fuse did its job. It sacrificed itself so the rest of the circuit could live to fight another day. The cause of the high current event must be investigated and resolved before a replacement fuse is inserted. If the error is still present upon repowering the system, the new fuse would follow its predecessor over the cliff. If a system is continually blowing fuses, you are wasting money and time feeding it more fuses. Fix the problem. Do not think for a moment inserting a fuse with a higher current rating is an acceptable solution to this problem. Current in the circuit will reach this higher, potentially more dangerous level, and then the fuse will blow again. Additionally, do not think by jumping or bypassing the fuse with a wire will the system function as intended. Without circuit protection, the system will burn itself to the ground. Circuit protection exists for a reason. It is not to be bypassed. There's not a lot more to say about fuses except this. Fuses are non-reusable devices designed to protect the system from high current. They do not protect operators from leakage current. I'll return to this point in a moment. Let's now briefly discuss the next circuit protection device, the circuit breaker. A circuit breaker is a circuit protection device very similar to a switch in that it is a two-terminal device placed in series or in line with a load it is intended to protect. Here's a simplified version of the schematic symbol for a circuit breaker. When the contacts are closed, a circuit breaker presents no opposition and current can flow through the system. Conversely, when the contacts open, the circuit breaker presents infinite opposition and current cannot flow through the system. A more sophisticated schematic symbol of a circuit breaker illustrates the moving contacts that make and break connection in series with one or more means of detection. The dashed line indicates that when the detection mechanisms detect a high current event, it signals the contacts to open. Additionally, a manually actuated switch allows a user to selectively close and open the circuit breaker just like a switch. Circuit breakers operate similar to switches, even more so than fuses, because circuit breakers can be reused and reclosed after they've opened. When the circuit breaker is closed, the circuit operates as intended. If, however, current reaches a certain predetermined value for a certain amount of time, the circuit breaker trips or pops and the contacts open and stop current flow. In contrast to fuses, after the error that induced the high current event has been cleared, the circuit breaker can simply be reset without the need to purchase another expendable item. Similar ratings such as rated current and rated voltage and interrupt rating exist for circuit breakers, as they did with fuses. For extreme cases, slow-blow fuses and circuit breakers could be paired in series with the element they intend to protect. In this case, the circuit breaker should have a rated current below that of the slow-blow fuse. In the event of an overcurrent event, ideally the reusable circuit breaker will trip first and open. If, however, the circuit breaker fails to open, the overcurrent event will approach that of the fuse, which melts. The double layer protection uses the reliable fuse to back up the reusable circuit breaker. In addition to reusability, circuit breakers offer other advantages over fuse. Industrial power is not limited to DC. We'll examine single-phase AC and three-phase AC later in this lecture series. For now, consider three-phase AC as three separate sources working in combination to service a single load. Compare and contrast a ganged three-phase AC circuit breaker and three independent fuses used to protect a device. The ganged circuit breaker is a single point of control that opens or closes all three lines simultaneously. The three independent fuses, not so much. One fuse could blow, and the other two fuses could still function, leading to an undesirable upsetting of the phase balance between the three separate phases known as single phasing. Single phasing is normally associated with high current draw, reduced performance, and a uniquely horrible sound produced by a three-phase AC motor. Here's a circuit breaker removed from a circuit. In its closed position, the circuit breaker presents almost no opposition to current flow. When it's automatically or manually tripped, it opens and presents an infinite resistance through which no current can flow. Unlike the fuse, though, the circuit breaker can be reset into its closed position. When a circuit breaker opens due to a high current event, you'll often hear an audible snapping sound. This rapid and forceful opening is a means of extinguishing the electrical arc between the moving contacts as they're pulled apart. Additional precautions are often used to minimize this arc. Larger circuit breakers use arc chutes to cool and divide the arc. Blowout coils or other magnetic means deflect the arc into the arc chute. Gases with a strong dielectric strength, a property we'll discuss later, like sulfur hexafluoride, SF6, quench the arc in gas circuit breakers. Vacuum circuit breakers have nothing inside them to ionize in the first place, and the arc is extinguished upon opening. Opposite to this methodology, an air circuit breaker uses compressed air to blow out the arc like a birthday candle. All these methods share the same goal. They terminate arc current very quickly. Circuit breakers often work in coordination with other circuit breakers in a larger electrical distribution system. We'll explore parallel circuit properties in later lectures. However, consider this simplified explanation. Consider a 120 volt source with a single master circuit breaker rated to open at 50 amps, which feeds several other circuit breakers of different ratings. Let's say a single 20 amp circuit breaker and 3 10 amp circuit breakers. In any particular subcircuit, as long as current remains below the rating of the circuit breaker protecting that subcircuit, that circuit breaker will remain closed and that branch will remain operational. If, however, current in any particular subcircuit exceeds the rating of that circuit breaker protecting that subcircuit, that circuit breaker and that circuit breaker only will open and disconnect that branch and that branch only. For example, let's say the 20 amp circuit breaker services an oven that is presently drawing 12 amps of current. The first 10 amp circuit breaker services a light that is presently drawing 1 amp of current. The second 10 amp circuit breaker services an outlet that is presently drawing 2 amps of current. And finally, the last 10 amp circuit breaker services another outlet that is presently drawing no current. In this scenario, the oven, light, and first outlet are all drawing current less than the rated current for each circuit breaker protecting each branch, and each branch functions as intended. The master circuit breaker experiences 12 plus 1 plus 2, or 15 amps, well below the 50 amp rating, and remains closed. Consider, however, a scenario in which the second outlet experiences a short and suddenly draws in excess of 10 amps. That circuit breaker and that circuit breaker alone opens, disabling that branch. However, the remaining subcircuits remain functional. This arrangement also allows technicians to isolate functional areas while servicing a system. For example, if the technician was tasked with servicing the 20 amp oven and the oven only, the 20 amp circuit breaker could be opened, locked out, and tagged out, and the service performed. While the oven is down for service, the lights and outlets remain functional. We'll examine more details of parallel circuits in later lectures. As was the case with fuses, there's not a lot more to say about circuit breakers except this. Circuit breakers are reusable electromechanical devices designed to protect the system from high current. Fuses and circuit breakers do not protect operators from leakage current. More on this point in a moment. Before we discuss operator protection, let's briefly discuss system and equipment grounding, bonding, and equipment grounding conductors. Fair warning, I am as eager to engage in a protracted discussion about NEC regulations as I am to throw stones at an angry hornet's nest. You cannot use anything in this or other lectures as professional electrical advice. Follow the rules. Follow the code. It's there for a reason, to protect people and property from fire and electrical hazards. In addition to serving as a handy reference point for voltage measurements, ground actually serves as a means of protecting people from becoming an inadvertent path for electrical current. Intentional grounding is the purposeful introduction of a ground connection to ensure the safety of operators and the proper operation of protection devices like circuit breakers and fuses. Unintentional grounding, in contrast, is a fault condition and needs to be quickly detected and resolved by circuit protection devices. Allow me to demonstrate. Consider a negatively grounded 120 volt source and an electrical device modeled as a 60 ohm resistor. An application of Ohm's law demonstrates the device draws 2 amps of current while in operation. Given the current drawn by the device is below the rated current, the circuit breaker remains closed and the device functions as intended. By referencing the negative terminal of the voltage source to ground, this is known as system grounding. Let's say this device is mounted in an electrically conductive metal frame. This could be a washing machine, a kitchen appliance, a motor, or anything electrical meant to interact with humans. The innards contain the electrically active components not safe to touch, whereas the frame and buttons servicing the machine should ideally remain electrically neutral and safe to touch. If a conductor servicing the electrical innards of the machine accidentally made contact with a conductive frame, the frame would now be energized. If the frame did not have a return path to the source, let's say because it's resting on rubber feet or an insulating pad, it's sitting there like a 120-volt snake, coiled and waiting, ready to bite the next person that tries to touch it. Any unfortunate person bridging the accidentally electrified frame and ground completes a conductive path. Let's say this unfortunate person draws 30 milliamperes of current, an extremely dangerous, painful, and damaging amount. The source supplies 2 amps to the device and 30 milliamperes to the operator for a total of 2.03 amps. Despite this dangerous occurrence, the rated current of the circuit breaker servicing this machine is not exceeded, and the circuit breaker will not trip despite the obvious safety hazard. Again, a traditional circuit breaker only protects the system from overcurrent events typically associated with short circuits. A very simple modification to this system could prevent such an unfortunate occurrence from ever occurring. This simple modification is the other aspect of grounding, known as equipment grounding. An extra wire, known as an equipment grounding conductor, intentionally connects the device's conductive frame to ground. In this case, the frame is additionally bonded, which is the permanent establishment of a low resistance path to ground for something like a frame that doesn't normally carry current. With the system and equipment grounded in this fashion, if an uninsulated energized wire does happen to make contact with the conductive frame, there now exists an extremely low resistance path to ground. High voltage, low resistance. The circuit breaker immediately opens because current quickly exceeds the rated value. The accidentally energized frame is immediately de-energized, saving the operator and system from damage. In addition to saving operators from inadvertent shock hazards, the equipment grounding conductor, by electrically connecting the frame to the reference plane upon which operators stand, also limits something known as a touch voltage to that same ground potential. This allows any accumulated static charge on a device to bleed off to ground. In summary, bonding the frame to ground purposely creates a low resistance path to ground, so overcurrent protection devices like fuses and circuit breakers can operate as intended, and operators always touch things at the same potential as that which they are quite literally standing on. While system and equipment grounding does keep the external frame of devices touch safe, it should be noted that it does not protect an operator if they accidentally make contact with the energized electrical innards of the device. Let's say the device draws 2 amps as previously, and an operator reaches inside the electrically neutral frame and touches the energized electrical innards. Let's say this unfortunate person completing a path draws 30 milliamperes of current, an extremely dangerous, painful, and damaging amount. As previously, despite this dangerous occurrence, the rated current of the circuit breaker servicing this machine is not exceeded, and the circuit breaker will not trip. Again, a traditional circuit breaker only protects the system from overcurrent events associated with short circuits. It is for this reason ground fault circuit interrupters, or GFCIs, are employed. A GFCI is a special type of fast-acting circuit breaker designed to shut off electrical power in the event of an unintended leakage path to ground. It works by comparing the amount of current going to and returning from equipment along the circuit conductors. You'll note in this scenario, 2 amps plus 30 milliamperes, or 2.03 amps, is leaving the source positive terminal. However, only 2 amps is returning to the source negative terminal, and 30 milliamperes is leaking through the operator to ground. A GFCI recognizes the imbalance between outgoing and incoming current and quickly opens the circuit, sparing the operator from further pain. The GFCI in this scenario acts like a traditional circuit breaker in that the open or closed state of the GFCI influences the fundamental on or off state of the system. However, GFCIs differ from a traditional circuit breaker in that instead of detecting unusually high current, the GFCI opens upon detection of an imbalance between outgoing and incoming current. Even a small difference, on the order of 30 milliamperes in this example, will make a tremendous difference to an operator's level of comfort. Before we move on to our last circuit protection device, the overload relay, allow me to reiterate a statement I made at the beginning of this lecture. You are a circuit protection device. This simple act of not doing stupid things ensures the safety of equipment, yourself, and coworkers. There are good ways and bad ways to build systems, and you need to be aware of potential safety hazards. Case in point, compare and contrast high side with low side switching. You will note a break or open anywhere in a series circuit halts all current flow through that series path. Perhaps one of the most important applications of this property is the ability to turn a circuit on or off at the flip of a switch. Consider a switch between the positive terminal of the source and the top of the electrical load. This is known as a high side switching arrangement, where the state of the switch selectively connects or disconnects the series elements to the source. In summary, switch open, everything's off. Switch closed, everything's on. Alternatively, consider a switch between the bottom of the electrical load and the grounded negative terminal of the source. This is known as a low-side switching arrangement, where all series elements are always hooked to the source. However, the state of the switch selectively connects or disconnects the return path to the grounded negative terminal of the source. As previously, switch open, everything's off. Switch closed, everything's on. Although low-side switching arrangements are functionally equivalent to high-side switching arrangements, they are perhaps not the safest means of doing so. Allow me to demonstrate. Compare and contrast the behavior of these two systems when some errant conductive object accidentally makes contact with the electrical load and ground. Let's say this electrical load is some motor designed to cut a full-grown Doug fir into 1,000 toothpicks. Obviously a device you want to keep an eye on when working in or around it. For obvious reasons, the switch needs to be open to ensure the device doesn't suddenly jump to life. In the high-side switched arrangement, an accidental connection of the load to ground does not energize the load because the load is already at ground potential due to the system ground connection and open switch. Not so in the low-side switched arrangement. The electrical load is always connected to the source and only necessitates a connection to ground to run. Any errant connection to ground can energize the electrical load even if the low-side switch is open. Be extremely careful when working around low-side switched elements. Alright, now that we've got a basic understanding of fuses, circuit breakers, system and equipment grounding, and GFCIs, let's introduce another related protection device known as an overload relay, which acts a little differently than the devices we've thus far discussed. An electrical overload is an event where a device draws higher than normal current, but below the rating of a chosen circuit breaker. If experienced only infrequently, an overload would be no cause for concern, but could become extremely hazardous if sustained for any length of time. An example of an overload condition might be an electrical saw hitting a knot in a piece of wood. If the circuit breaker was undersized, the system would experience what is called nuisance tripping, and every time the saw hit a knot in the wood, the circuit breaker would open and need to be reset. Not the most ideal of situations when saws are routinely asked to cut through imperfections in wood. Overload conditions only become harmful if they're sustained. For example, when a saw becomes bound in a piece of wood and you just let it sit there. High sustained current can heat up the wires and damage the insulation on motor windings. It is for this reason overload relays protect systems not from high current events associated with short circuits, but rather from sustained high current draw, where the key word is sustained. An overload relay will allow a motor or other device to briefly overload, but only for a given amount of time, before it signals enough is enough. Motor starters, relays, and ladder logic are a little outside of the scope of our present level of understanding, and we'll return for a more thorough discussion of these concepts when we move into the motor control series much later. However, I would like to just touch on the basics of overload relays because they're pretty neat devices. The schematic symbol for an overload device looks like a pair of opposing question marks. Long story short, an overload is a detection device only, and it does not actually break connection to the source. The actual act of making and breaking connection is reserved for devices like circuit breakers and contactors, a type of heavy-duty electrical switch. The overload in series simply tells the device under its direction to do so when it experiences a sustained overload condition. Here's a diagram of a three-phase manual motor starter with integrated magnetic and overload elements. You'll note the schematic symbol is almost identical to a circuit breaker. Here the overload elements serve to detect sustained current draw and tells the contacts to break connection. Here's another system incorporating an overload relay in series with a magnetic contactor. Again, the overload elements only serve to detect sustained current draw. When this occurs, the overload relay tells the contactor to break connection via means of pilot control known as ladder logic. We'll examine ladder logic and motor control in later lectures. The means overload used to sense this excessive current draw are pretty creative. One method uses a strip made out of two different metals, hence the name bimetallic strip, with two different expansion rates. When heated from excessive current draw, one side expands at a different rate and mechanically opens a switch. This normally closed switch, now being held open, tells the low voltage control circuit to open the high voltage contactor. A second method uses a metal alloy that passes directly from the solid state to the liquid state at a certain temperature, without the malleable lumpy intermediary. The solid state retains a spring-loaded switch, but when it enters the liquid state, it lets the spring move, and this switch is what again signals the control system to open the contactor. The third overload detection method uses digital means, think a really small computer, to monitor current and signal the control system in the event of sustained high current. Overloads, regardless of their means of operation, after being triggered need to be reset for the device to operate again. The overload, like a circuit breaker, and unlike a fuse, is a reusable device. Sometimes this reset is performed automatically, or it must be done so manually, requiring human intervention. The time period between triggering and automatic reset allows the overload element to cool. Due to the cumulative nature of heat, overloads that have been triggered once will trigger earlier subjected to the same overload. Repeated overloads are a clear sign the motor is undersized for the task. Do not think for a moment we're done discussing the overload relay. We'll return to a far more thorough discussion of motor starters, contactors, and overload relays in much later lectures in motor controls. For now, you can think of an overload as a circuit protection device that allows temporary excess current draw, yet signals another element to open if it detects sustained excessive current draw. In contrast, circuit breakers and fuses interrupt extreme current draw, typically associated with short circuits. This wraps up our discussion of common circuit protection devices. Let's compare and contrast the devices we covered one last time. Both fuses and circuit breakers open when current draw is in excess of the rated value. A fuse is expendable and reliable. Conversely, a circuit breaker is reusable, yet more complicated. System and equipment grounding ensures the proper operation of circuit protection devices like fuses and circuit breakers, and ensures the external conductive surfaces of electrical devices remain touch safe. A GFCI is a special type of circuit breaker that detects imbalance between incoming and outgoing current in a circuit and interrupts the circuit if it detects leakage. Finally, an overload relay allows brief overloads but protects against sustained overloads. An overload relay is a detection device only, and it signals another device, like a circuit breaker or contactor, to actually make or break connection. Finally, and most importantly, you are a circuit protection device. Pay attention to current. Always operate devices inside their intended range and avoid sustained overload conditions. Know where the emergency off switch is and make sure you've got access to it at all times. In conclusion, this lecture took a close look at basic circuit protection devices. We introduced fuses, circuit breakers, overloads, and GFCIs and discussed their intended purposes, means of operation, and differences between them. Additionally, we discussed the use of system and equipment grounding, bonding, and equipment grounding conductors used to protect people from electrocution hazards. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.